Good evening. Hello. Welcome to Skeptics in the Pub Online. I'm Gerald from Skeptics in the Pub. Good evening alone in Germany, and it's great to see so many of you online tonight. Sorry, a friend of mine wanted to see whether you're all still here. I don't have any scripts for him to play out this week, but I told you they're all still there. So, you happy now? Thank you. Okay, Skeptics in the Pub. We used to meet in various pubs around the UK and further out, but this is the age of COVID-19, so we put our heads together and started these online talks, which quickly grew into a lovely community with our own Discord server and various channels on social media. If you want more details, watch out for our chat moderators providing the links repeatedly throughout the evening. Our events follow the usual order. We will have a talk followed by a short break for refreshments, comfort breaks, and then closing out the evening with a Q&A with our speaker. If you want to ask a question, then go to sitp.online/ask, where you will be able to ask your question, upvote questions that already had been asked, and have a look around. You do not need to have an account, but you can add your name, and it would be lovely to have your name next to a question so we don't have to pretend every question is from somebody called Anonymous. Good. Let's talk about tonight's speaker. You might know her as Alice from Skeptics with a K. You might have seen her here as MC for some of our talks. Or you might know her as a prolific blogger and deputy editor of the UK Skeptic magazine. But we want to give her the full and appropriate credit. Dr. Alice Howarth is a research academic working in pharmacology and therapeutics at the University of Liverpool, where she studies the pharmacokinetics of nanomedicines. She is vice president of the Merseyside Skeptics Society and in 2019 joined the board of organizers of the QED conference. Alice has written for The Guardian and Breast Cancer Now, and she also blogs at dralice.blog. On the Skeptical podcast, Skeptics with a K, she talks about cancer, medical pseudoscience, women's wellness products, and other topics. She also lectures on cancer and women's wellness for skeptical groups across the world. In fact, this is the second time that I have the honor and pleasure to introduce Alice, as she was so kind to also give a talk to our group in Cologne a few years ago. So, let's get started. Please put your hands together in the chat for Dr. Alice Howarth.
Oh, thank you very much for such a lovely welcome. And yes, you're right. I did speak for Cologne. It was November 2019, and it was one of the last times I gave this talk. So bear with me, this might be a little bit rusty because I've not given the talk for a very long time. But this is, this is the talk that I kind of put together after years of, I did my PhD in cancer research, and after years in working in cancer research, I would talk to people about the kind of work that I do. They'd ask me questions about what my job was and what I would do. You get in a taxi and the taxi driver would ask you, remember when we were getting taxis? The taxi driver would ask you if what your job was, and I would tell them, I work in cancer research. And the question that they would almost always ask immediately afterwards was, so come on then, do we have a cure? Are we nearly there? Are we ready to really treat cancer well in all patients that encounter it? And of course, it's a complicated disease. It has a lot of different answers to that question, and the answer would always be in that taxi setting. It's complicated. I'm not sure I can give you an answer in the duration of a taxi journey. But what I did want to do was put together a talk that would actually answer that question and talk through some of the complexities of what cancer is, how we treat it, and what are the risks of oversimplifying cancer and the propensity for people to perhaps go down the cancer pseudoscience route. So that's what I'm going to talk to you about today. I'm going to start with what cancer is, and then I'm going to talk to you about how we treat it, and then I'm going to talk to you a little bit about some cancer pseudoscience. But firstly, why are we interested in cancer? Why do I want to tell you about the complexities of cancer? I'm sure I don't need to tell you that this is a really common disease. In fact, 1 in 2 people born after 1960 in the UK will be diagnosed with some form of cancer in their lifetime. So that means if it doesn't affect you in your lifetime, it's going to affect someone you know. It's going to affect one of your loved ones, and you're going to encounter this disease at some point. It's important to a lot of people, and we need to understand the complexities of this disease. And in fact, this risk of being diagnosed with cancer at some point in your lifetime has been rising over the last few decades. So if you see on this graph here, from in the 1930s, if you were born in 1930, your risk of developing cancer at some point in your lifetime was around 1/3. And that's jumped up to now, if you're born after 1960, your risk of being diagnosed with cancer in your lifetime is up to 50%. And actually, there's a slight difference there between men and women, with men slightly more likely to be diagnosed with cancer in their lifetime than women. So what is cancer? Hopefully, I'm not telling you something new to tell you that humans are made up of organs, and organs are made up of cells. So we've got lots of different cells in the human body. We've got lung cells in the lungs, liver cells in the liver, lots of different types of skin cell in the skin, and different types of muscle cell in the muscle. In fact, we have 37.2 trillion cells that make up one human being. So on your screens now, you can see that's 37.2 with that many zeros after. It's an awful lot of cells. But not only do we have this many cells in the human body, we have to have lots of different types of cells that are doing lots of different types of things. So this is a list only of cells that secrete stuff. So that's the salivary glands in the mouth, that's mammary glands that secrete milk, that's sweat glands that secrete sweat. Only cells that secrete something of some kind. That's that list. That's how many different types of cells we have that do that job. And of course, that's quite a niche job that the human body has to actually do. So of course, it's going to be very complicated to have lots of different types of cells doing lots of different types of things. So they all look slightly different. But broadly, they all have some similarities. So there are a few cells that don't fit this convention, but broadly, a typical cell looks something like this. You've got a membrane on the outside of the cell, and then in the center, you've got a nucleus where the DNA sits, and then you've got a lot of mini organs, if you like, in the cell, or organelles. So these are the structures that allow the cell to do its job. So you've got things like the mitochondria there in blue, which provides energy for the cell. And then we've also got things like the lysosome there, which is almost like the stomach for the cell. It's an acidic body that breaks things down and allows the cell to reuse the things that it's broken down. So humans are made up of organs. Organs are made up of cells. And cells need to be able to communicate with each other in order to do their job. So they need to communicate in lots of different ways, and this communication allows them to identify different things. So it allows them to know what type of cell they're supposed to be. For example, so you want your lung cells to know how to be a lung cell. They've got a very specialized job. They need to know that they are a lung cell. They need to know how to grow, when to stop growing, how big to grow. And this can also give us body and organ size based on how the cells grow. They also need to know how to divide. So when cells are growing inside their organ, they grow to a particular size, but you need a certain number of cells to build that organ. And so they need to multiply so that you've got multiple different types of cells. They need to not multiply out of control. They need to multiply to the level that they're supposed to and then stop. So they need to communicate that. They need to communicate with one another. So the best example of this is in the heart. When you want your muscle cells in the heart to all contract together, they need to communicate with each other so that they all contract at the same time, so your heart beats and pumps blood around the body. They also need to communicate to know where they are. So it's all very well and good your lung cell knowing how to be a lung cell, but if it's sitting in the liver, it's doing something wrong. It needs to know that it's in the right location doing the right thing. And then you also need to know, the cells need to know how to die or when to die. This happens a lot in development. So for example, the webbing between your fingers and toes, that dies away during development. So it's really important that cells can communicate with each other properly. And all of this allows them to build up into the organs and allows the human body to do its job. But in order to communicate with each other, they need to have some kind of communication system that allows them to do that. So in cells, this is proteins. Proteins allow cells to communicate with each other. And proteins are created from a recipe book in the human DNA. So inside the nucleus of every cell, you've got your DNA, which is sometimes structured into 23 pairs of chromosomes, and sometimes it's just kind of floating around free. And on each piece of DNA, we have these small regions that are referred to as genes, and that individual gene is a recipe for an individual protein. There's other stuff in your DNA that does other things as well, but a good chunk of our DNA is dedicated to creating proteins from these individual genes. So the central dogma is that we have, a long piece of DNA that has individual genes on it that are a complicated structure made up of 4 bases, which we label A, T, G, and C. And these DNA bases are organized into what we call codons. So they're into little repeats of triplicates where you have 3 letters, which are one single codon. And inside the cell, when you want to create a protein, you take that DNA and you convert it into a very similar molecule called RNA. And then after that, you convert it into a protein. So each of these codons is a code for a single amino acid, and amino acids are your building blocks of your protein. So you've got multiple amino acids that build up into a single protein, and then these kind of fold up and get into the shape that they need to be, and you've got a protein that can do its job. So the human genome has more or less 20,000 genes, which means it codes for roughly slightly more, slightly less, depending on the gene. Some genes code for multiple proteins, but roughly 20,000 proteins. This isn't 20,000 proteins. This is a lot of proteins, and I do not need you to understand this slide. This slide is incredibly complicated. I'm not going to explain it. You do not need to understand it. But this is to show you how complicated the inside of a human cell is. So normally I would have a pointer here that I can show you what everything is, but just to describe it to you, right at the top there, you've got a barrier made of 2 layers. So that's your cell membrane. That's where the cell ends. It's the outside of the cell. And crossing that membrane, we've got proteins that span from the outside of the cell to the inside of the cell, and that allows these messages to be passed from the outside to the inside. Once a message is passed from the outside to the inside, you get these step-by-step reactions of proteins interacting with each other and triggering changes in each other as they move their way through these complicated signaling pathways and cause a thing to happen in the cell. And often what that thing is that the message gets all the way through into the nucleus, which is down here in the bottom, also surrounded by a grey membrane. And it causes new proteins to be made, proteins to be upregulated, proteins to be activated, different things to happen that changes how the cell behaves and allows it to do its job, whatever its job might be, wherever it is. All of this is happening inside every single one of those 47.3 trillion cells in the human body. And it's cram-packed inside around all these organelles in the cell. It's a very, very busy place. So that's how a normal human cell works. And obviously, that's incredibly complicated. But then we need to understand what cancer is. So cancer in its very simplest form is just cells growing out of control. And we'll come back to what that means for the proteins. But the very simplest description of it is that it's cells growing out of control, cells growing where they shouldn't do, growing too much. And because, as I've already told you, we've got so many different types of cell, it means we have so many different types of cancer. In fact, we have over 100 different types of cancer. We try to organize them roughly by cell type. And some cancers of certain cell types behave similarly to each other. But we've got hundreds of different types of cancer. It's hard to really find anything unifying about them sometimes, but we have identified a few things that they do have in common. So this is from a very famous paper called The Hallmarks of Cancer, where they identified these things that make a cancer. So cancers have sustained proliferative signaling. This means that they can divide as many times as they want. They never stop. They evade growth suppressors, so they continue growing constantly. They can avoid immune destruction. They are essentially immortal. They never stop dividing. They promote inflammation. They actively invade and metastasize. So they're really motile. They're really good at moving around the body and breaking into blood vessels and spreading around the body. They do an interesting thing called they induce angiogenesis. So when a tumor gets really large, the cells inside the center of the tumor need to bring nutrients to that central part because there's so many cells there that they struggle to get enough nutrients. So they generate their own blood vessels to bring blood into the tumor and grow these blood vessels to bring those nutrients that they need. They have genetic instability. They're prone to acquiring new mutations, again, which I'm going to come back to at a later point in the talk. They resist cell death. So when we know that they need to die, they don't do that. They can evade that. And they generate energy in a slightly different way to a normal cell. And broadly speaking, it's mutations that cause cancer. So it's mutations in the DNA that causes a change in the protein, a change in these proteins that cause the cells to grow out of control. So that might be a mutation in a single protein. It might be a mutation in an oncogene or a tumor suppressor. So to explain what an oncogene is, this is a slightly simpler signaling pathway. This is actually taken from my PhD thesis. So here we've got the cell membrane up at the top there again with a double layer, and we've got a single protein spanning across that membrane. From there are two signaling pathways with different proteins that are involved in them. You don't need to know what the proteins are, but they trigger either proliferation, so multiplication of the cells, or cell survival. And the oncogenes are these things that promote that pathway. So there's a few key proteins in these pathways that activate those pathways. And if you get a mutation in one of these proteins that makes the pathway super active, then you are going to get either too much proliferation, too much cell survival, and you're going to cause the cancer cells to grow out of control. So you'd have an activating mutation in these particular proteins. When it comes to tumor suppressors are usually the proteins that are switching these pathways off. So here we've got one called P10. Again, you don't need to know what that does, but what it does is turns the pathway off, turns that constant cell survival pathway off, dampens down the signal, helps keep everything regulated as it's supposed to be. So if you get a cancer-causing mutation in one of these tumor suppressor proteins, you've deactivated the protein, and now you've got this pathway continually turned on. There's nothing to switch it off, and the cell is surviving indefinitely. But in reality, actually, you might have a mutation in one of these proteins, one oncogene or one tumor suppressor, but in reality, actually, we often have a mutation in several proteins, both within the same cell and across different cells within the tumor. So every cell in the tumor might look slightly different to the other because they're prone to acquiring new mutations as they develop. And this is shown in this graph here. Again, you don't necessarily need to follow all of the details here, but just to show that we've got a number of mutations up on the y-axis here, and we've got a list of different cancers on the x-axis. So down here at colorectal cancer, we've got between 500 and 1,000 mutations per tumor. So that's around 750 mutations per tumor in colorectal cancers. We go all the way down through some adult solid tumors, which have somewhere between 75 and 25 mutations per tumor. And then we go down to the pediatrics, where often actually it's a single mutation. And that can often be why we treat pediatric cancers quite well, because we know what the single mutation is that's causing that cancer. So we have multiple mutations per cancer, and that'll be in multiple different cells, and we need to understand which is the mutation, which is the important one, which is the one that's really driving that cancer to grow out of control. We know that they look different to normal cells. They've got lots and lots of different mutations, but only a handful might be important for actually driving that cancer forward. So there's a paper recently that showed that actually, although we might have hundreds of mutations per tumor, there's only 1 to 10 driver mutations in most tumors. Actually, on average, there's 4 mutations that are driving a cancer forward. So we're kind of looking for a needle in a haystack. We need to know exactly what mutation is causing that cancer. So hopefully now I've given you a bit of a picture for what cancer is. It's a case of proteins going wrong and cells growing out of control. And now I'm going to talk to you about how we treat it. So we have, broadly speaking, 2 different types of treatment. We have our general anti-cancer treatments. These are drugs, surgery, or radiation, where the goal is to kill anything that looks like cancer. We're not very specific and elegant. We're just cutting the tumor out, or we're radiating it with radiation, or we're using a very generalized drug that targets maybe cells that are particularly proliferative. And it'll kill anything in your body that is particularly proliferative, but the cancer cells are very, very good at that. So the drugs will target those. So there are general anti-cancer treatments, but we also have more recently, we're working towards more specific anti-cancer treatments. So these are drugs that are really fine-tuned to the specific mutations that the tumor you have actually has. Or these might be things like immunotherapy, where we're trying to target the specific tumor that the patient has. We're learning about that tumor, we're learning about which mutations are involved. So if we go back to our example of oncogenes, so I told you before that these are proteins that are promoting the proliferation or cell survival pathways or other pathways in the cell. And in cancers, they're often hyperactive. They've been switched on and they're permanently on and they never get switched off. So we can design inhibitors that target those specific proteins and switch them off. And usually at this point, I would tell you that this protein here, RAS, although we would love to be able to treat it because it's mutated in 20% of all cancers, we have dubbed this protein the undruggable kinase because we've never, in the decades that we've known about it, we've never been able to find a drug for it. And very recently, in the last couple of months, a company has actually published data that they have found an inhibitor that specifically targets this protein. And we're hoping that we can use this to treat a large portion of cancers that have a mutated version of this protein RAS. When it comes to tumor suppressors, I told you before that these proteins, if they're causing cancer, the problem is that they're less active than they should be. So we don't really have drugs that can switch it back on. But what we can do is try to understand the pathway and see what that protein is opposing. So in this case, P10 is reversing the action of another protein called PI3 kinase. So what we can do is try to inhibit that protein. So we give the patient a drug that blocks that protein, and that switches off that cell survival pathway and allows the tumor cells will then be killed by this. Often the tumor cells are quite dependent on these pathways. So as soon as you inhibit that single protein, the cells start to die off. And broadly speaking, we're doing really, really well when it comes to cancer survival. We now have cancer survival rates for 10 or more years of up to 50%. That's doubled in the last 40 years. And that's despite there being quite a large variation between different cancer types. So, for some cancer types, we're really very good at treating them. And we're up to the point of there's the high 98% 10-year survival. So to finish up on cancer treatments, I'm going to take you through a bit of a case study because it illustrates a point I want to make about these cancer treatments. So again, you don't need to know or remember all the details, but in the case of chronic myeloid leukemia, we identified a long time ago that we know 80% of all people with chronic myeloid leukemia have a mutation in a gene that causes the creation of a protein that does not exist in a normal healthy cell. It creates this protein called BCR-ABL, brings two genes together that shouldn't be together and creates this entirely new protein. It doesn't matter what BCR-ABL does to cause cancer. We know that it does cause the cancer. And we know that it does this by binding to a substrate. So it binds to a substrate and causes cancer. So we realized that this was the case, and we used some very clever chemistry to understand how we could block this. And we designed a drug called Gleevec. Gleevec competes with the substrate, binds to the protein, and the protein becomes essentially inactive. It can't do its job anymore. But I told you before that cancer is particularly unstable. It has a lot of it tends to acquire mutations. And so in patients with CML, this is what happened. They would acquire a mutation in that protein that would prevent the drug from binding, but allow the substrate to bind. And that caused drug resistance. Now, luckily, we understood how the protein worked, we understood how the drug binding worked, and we could design second and third line treatments that patients could go on. And the idea is maybe we don't cure this cancer, but we can switch patients on to new treatments so that they live a healthy, happy life. And this is where science is really important, because not only do we want to have treatments that will last for a lifetime, if we're keeping patients on treatments that last for a lifetime, we also want to minimize the really nasty side effects that some of these treatments can have. So one of my favorite, maybe slightly not so recent findings, although this is still a really exciting area for research, piece of science that came out a few years ago was this piece of research where there was a group that was looking at treating tumors with cancer drugs, and they wanted to protect the healthy tissue. They wanted to just target the tumor. Normally, when we're taking drugs, they're affecting proteins that we do have in our normal body. They're just doing something different in the cancer cell. So you still get nasty side effects. So in this case, they wanted to wrap the drug up in nanobubbles, nanoparticle structures made up of little microbubbles. They could float through the blood, completely protecting the healthy tissue from this drug. And when it reached the tumor, they could use very specific ultrasound that targeted only the tumor to break those microbubbles up, release the drug, and allow the drug to pass into the tumor. The idea being that this would minimize side effects on the healthy tissue, but get the drug directly to the tumor. And this is working really well in mice, and hopefully is something that can be taken forward to be used in humans. Another really cool thing that science has been working on, and I took this slide out because Zika virus stopped being interesting. But then actually, I think it's interesting again to illustrate this when we're living through the COVID pandemic. So if you remember a few years ago, Zika virus was a big cause for concern, particularly because it was causing problems with development in babies and affecting their brain. So we know that the Zika virus is really good at getting into the brain. And when it's in the brain, it kills cells. And we know that this is a problem for babies in development, but it wasn't really a problem for adults. So researchers recognized that actually this virus gets into the brain and it kills cells. What does it do to cancer cells? They figured out that Zika virus can kill cancer cells in the brain. We've got brain tumors that we find very, very hard to treat. So researchers started looking at how can we first, obviously, mutate the virus so that it's not going to cause any symptoms and it's not going to be infectious at all, because that would be a disaster. But we're going to see if we can find a way to use this to treat these very rare forms of very severe brain cancer, using a virus that exists that we know gets into the brain really well and we know can kill cancer cells. And again, this is ongoing research that's really interesting, and it'll be interesting to see if we find any other viruses. We know there are some viruses that kill tumor cells, and if there are any other viruses that do similar things. Okay, so I've told you roughly what cancer is. I've told you how we treat it. But now I want to talk to you a little bit about cancer pseudoscience. But I'm going to start again with the science. So I'm going to talk to you about cancer and diet. It's a nice case study. We do know that when it comes to diet, there are some things that we can consider when it comes to cancer, less about treating cancer, but more about prevention. So this is an infographic taken from Cancer Research UK's website. They make some really beautiful infographics. And they say, when it comes to cancer and diet and prevention of cancer, we can do two things. We can try to keep a healthy weight, because we know that cancer is often linked to obesity, although we don't know how that is linked, whether there's a causal link or not. And we can cut down on things like processed and red meat. So this was actually due to a World Health Organization classification update way back in 2015, where they commented that processed and red meat might lead to increased risk in cancer. And of course, the media covered this in the way that the media tends to do, by talking all about how processed meats do cause cancer, that 2 rashers of bacon a day raises your risk of cancer to the same level as cigarettes, and that processed meats rank alongside smoking as cancer causes, and the bacon and sausages as big a cancer threat as cigarettes, World Health Organization report warns, and that bacon, ham and sausages as big a cancer threat as smoking, World Health Organization to warn. Of course, this was massively sensationalized. And the important point to illustrate here is that although we have good science, it's quite often reported quite inaccurately. So again, here we've got an infographic from Cancer Research UK that I think beautifully illustrates the difference between processed and red meat and cigarettes, because that was what the media was comparing it to. So in this case, we can see that cancers caused by tobacco, 86% of all lung cancers are caused by cigarette smoke or tobacco. And lung cancer accounts for nearly 20% of all cancers. So it's a very, very common cancer, and tobacco causes almost all of those very common cancers. Meanwhile, when it comes to cancers caused, bowel cancers that might be caused by processed and red meat, we know that it does increase your risk of bowel cancer, and that 21% of all bowel cancers can be linked to eating processed and red meat. But that's a much smaller figure. That's a fifth of all bowel cancers are caused by eating red or processed meats. And the number of all cancers is even smaller again. Only 3% of all cancers are bowel cancers. So that means that if no one ever smoked, we would have 64,500 fewer cases of cancer, whereas if no one ever ate any processed or red meat, we'd have 8,500 fewer cases of cancer. So, the media reported this very sensationally, comparing processed and red meat to tobacco smoke. Very different things, in fact, and a complete misunderstanding of risk. But of course, that doesn't mean that processed and red meat is linked to an increased risk of cancer. But what about cure? Do we think that a change in diet can help cure cancer? And this is where I'm going to talk to you about the pseudoscience. Normally at this point in my talk, I ask if anybody has heard of Gerson therapy. So please tell me in the chat if you have heard of Gerson therapy, because that's the case study I'm going to use. So Gerson therapy is a therapy, and this is just a little primer taken from the Good Thinking Society's website. They have loads of these on lots of different topics. This is the one that they have on Gerson therapy, and they say that Gerson therapy has the hourly consumption of organic or raw juices, extreme uses of supplements, and a daily schedule of up to 5 coffee enemas. Doesn't sound like a fun treatment. And in fact, it's also really expensive. So the setup cost for Gerson therapy includes £7,000 for a 2-week stay at the clinic. Again, this is from the Good Thinking's website. £1,600 for a Gerson juicer, £400 for a hydraulic press, £650 of organic produce, £650 of supplements, £325 for a distiller, and £20 in herbal teas. And additionally, each month you would pay £700 per month on organic food, £250 per month on organic produce for juicing, £200 per month on Gerson supplements, £20 per month of organic castor oil, £7 per month on enema pads, and £100 per month on Gerson doctor consultations. This is obviously incredibly expensive, but that monthly cost. I've seen a Gerson therapy practitioner recommend that you should be on this treatment for 2.5 to 3 years or longer for the rest of your life. So this is astronomically expensive. You might think, okay, if you've got the money, you could give it a go. All you're going to do is take some juices and do some enemas. Maybe that's not too bad. But actually, there are also health risks associated with this treatment. So we know that coffee enemas can cause infections, dehydration, fits, constipation, mineral imbalances, heart and lung problems, and even death. And these dietary supplements and juices can cause dizziness, abdominal cramps, loss of appetite, diarrhea, and sickness. Now, I first came across Gerson therapy a good few years ago now, in 2017, when we saw in our local newspaper, in the Liverpool Echo newspaper, this story: man with cancer beats 8-month prognosis despite shunning hospital treatment. This was a young man who at age 18 had developed stage 2 Hodgkin's lymphoma, and he'd had conventional treatment. He'd gone into remission, but the cancer had come back. At age 21, he was in the news. He was a local musician, talking about how he had decided not to go down the conventional medicine route and was taking Gerson therapy and other alternative therapies. And the newspaper article said, now, over a year later, the patient is thriving and his condition appears to be getting better despite not setting foot in a hospital since he received his diagnosis. My concern was that this is incredibly promotional about a treatment that has no evidence of efficacy. And I thought this was an incredibly dangerous message to send. So me and other people at the Merseyside Skeptics Society wrote a letter to the Liverpool Echo, criticising them for their decision to be very promotional. And it got published in the print edition of the paper. So here's a quote from that letter. We said, "The miraculous claims for alternative cancer cures make for impressive headlines, which are doubtlessly seductive, but as a responsible publication, you have a duty to your readers to put truth ahead of sensationalism. By promoting these so-called cures without scrutiny, the Echo lends these dangerous quackeries the legitimacy of the publication's well-earned reputation and promotes clear misinformation to some of its most vulnerable readers." So we managed to get a load of cancer researchers at the University of Liverpool to sign this letter, including the director of the Northwest Cancer Research Centre at the University of Liverpool. Of course, the next week they published a very similar article saying the same thing, but we were very interested to keep an eye on the Gerson therapy story. And a few months later, we saw that somebody promoting Gerson therapy was coming to Liverpool to give a talk. So in August 2017, there was a talk from this chap, Patrick Vickers, who was talking about his clinic called the Northern Baha Centre. And in the promotional material, they said, "The Gerson treatment continues to be the most powerful and effective alternative therapy available for advanced or non-advanced degenerative diseases, including terminal cancer." Of course, this was quite concerning, so we thought we'd go along and see the talk. So this is a photo that was taken on the day. In fact, you can see me in that photo, third row from the back, second person in with the ginger hair in a ponytail. We went to see we went to see Patrick Vickers give a talk on this. We counted about 70 people in attendance. The Gerson people said that they had 100 people in attendance. The ticket price is £20 to £30. And while we were there, we identified that a good proportion of the audience were cancer patients. It was run by this guy, Patrick Vickers, who runs the Northern Baja Gerson Centre in Mexico and is a chiropractor. Not qualified necessarily to be treating your cancer, but believes that he can cure disease. Is trained to believe that he can cure disease by cracking your back. So he said some very concerning things during his talk, and I don't want to misrepresent him, so I'm going to directly quote some of the things he said. So during his talk, he said, we're treating advanced terminal diseases, not just cancer, but virtually every single disease we're successfully treating. And in fact, he claimed to be able to cure cancer multiple times throughout the talk, something that I believe is breaching the Cancer Act, where nobody should offer to treat any person for cancer or prescribe any remedy or give advice in connection with the treatment, which includes any advertisement, which includes any notice, circular, label, wrapper, or other document, or any announcement made orally or by any other means of producing or transmitting sound. So for me, giving a talk in a hotel room, in a public venue that allows anyone to attend is an advertisement for curing cancer and is therefore in breach of this Cancer Act. He said, I'm telling you folks that the science is so crystal clear and it's so perfect that it's indisputable. Of course, I dispute the science. I don't think this is a treatment that works. There's no evidence that this is a treatment that works. But not only that, he repeatedly encouraged distrust in people who might dispute his claims. For example, medical professionals, friends and family, and other charitable or governmental sources of information he would say were not to be trusted when it comes to cancer and cancer treatments. When he was talking about his wife or fiance, he said so she had breast cancer. He said because she stuck with Gerson therapy, and that's the only reason why she's alive today, she had absolutely no chance of survival using all conventional medicine. And in fact, patients were warned over and over again that if there were any mistakes made in administering this really complicated treatment with hourly juices and the complicated requirements in terms of what sort of organic food was allowed, any mistakes made would lead to its failure, that the patients themselves were responsible for this treatment working. During the Q&A, he was asked, what is your take on conventional treatment? He responded that it's incompatible with Gerson therapy. He said, what would you say to someone who wanted to take it? He said, chemo is made from mustard gas, biological warfare. It takes you as close to death as possible, and after the cancer comes back, 10 times more aggressive. And in fact, patients were told directly to stop taking conventional therapy, advised not to take part in any clinical trials offered by the NHS, and that the conventional treatment was incompatible with Gerson therapy. There was a lady who told him what treatment she was taking for her cancer, with giving zero medical background on her case, and he categorically told her to stop taking that treatment. Patients were also encouraged not to have any scans for the first 6 to 12 months after starting the Gerson therapy treatment. And even when they were allowed to resume taking scans, they were told that they should take non-conventional pseudoscientific scans instead. This talk was one of the most dangerous things I've ever seen. And of course, as soon as we saw Patrick Vickers give the talk, we regretted not doing more to get it stopped. So when we saw Patrick Vickers coming back to the UK to give 3 more talks across different parts of the UK, again in Liverpool, also in Glasgow, and I can't remember where this third one was because this was a while ago, Wales somewhere, I think, we were very, very concerned that this talk was very, very harmful. And we worked together with some of the skeptics in the pub groups around the country, and we contacted both trading standards officers in the areas and the venues directly, and we managed to get all 3 of these events cancelled. But that was early 2018. Coming back to the story I told you before, the way we heard about Gerson therapy was for a young musician in Liverpool who had gone down the Gerson therapy route. And unfortunately, since then, this young man living in Liverpool has died from his cancer. So Sean was 23 when he died. He may well have the conventional therapy may well not have prolonged his life much longer. He may well have not survived regardless, but he was on the Gerson therapy treatment and other treatments and followed this route until his death. Last year, a journalist got in touch with us at the Merseyside Skeptics Society, asking if they could talk to us about it because she wanted to put together a documentary for the BBC. So this is that documentary. She talked very sensitively about the decisions that led to Sean going down that route, the things that were advertised to him. There's also another story she talks about in the documentary. But one thing that's really interesting that she discovered was that throughout Sean's treatment, and potentially the thing that actually led him into the Gerson therapy in the first place, was going down the thermographic scan route. So Sean had been led to believe that thermographic scans could identify whether he had cancer, how big his cancer was, and what his progression was like. So thermographic scans are scans that detect heat. We use them in lots of things. In fact, we're using them to test whether you have a temperature. If you're going to a venue and we want to know if you might have a fever, and reduce the risk of bringing in patients with COVID into a public space. And we use some thermographic type measurements to detect that. They do detect heat, and they do detect heat in the body. And the argument is that when you have a tumour in the body, it has its own vasculature, its own blood vessels, and therefore it's very hot, and you can detect a cancer using these thermographic scans. Now, there are many problems with this. Firstly, they tell you whether you have a hot spot in your body. They don't tell you whether that is cancer. They can't distinguish between, they can't tell you what that type of heat is. And also, not all tumours are hot. Some tumours are slightly warmer than the surrounding body. Some tumours aren't, so it misses tumours as well. So there's no reliable cancer professional that would recommend thermographic scans to monitor the progression of your cancer. But actually, it seems to be that there's an awful lot of people who are using these scans to detect progression on their cancer. Particularly, this is quite commonly offered as an alternative to mammary scans for women who might be at risk for breast cancer. And this is obviously incredibly concerning. So, hopefully, I've told you what cancer is, that it's a collection of complicated diseases that we don't fully understand yet. There are things about cancer, there's so many proteins involved that we don't know all the details about all the cancers just yet. I've told you that we treat it with evidence-based medicine that has reliable proof of efficacy which considers both resistance and normal disease progression. I've told you about cancer pseudoscience and how it can be incredibly dangerous, but sometimes hard to detect, especially if it relies on misrepresented science that might be misreported in the media. Here are some places you can find me. So I am part of the Merseyside Skeptics Society, and I do Skeptics with a K podcast. And then I'm also deputy editor of the Skeptic magazine, the UK version of the Skeptic magazine. There's my Twitter handle, website, email address, and some resources that I've used throughout this talk that I think are really worth checking out. Good Thinking Society has some great information on all sorts of different types of alternative therapy, and Cancer Research UK put together great infographics on cancer and really talk things through in details that anybody can follow. When cancer's so complicated, it's a real skill that they can do that, and it's always worth checking out their website. I think that's all I've got to say to you for now. I look forward to the Q&A.
Thank you very much. I hope there's a lot of cheering and applauding in our chat, but I'm actually quite sure of it. So we will now have a short break for drinks to be refilled, pits to be stopped, and other tasks to be completed as required. Short reminder, if you want to ask a question, the website is sitp.online/ask, where you can see all the questions that already have been put up, and you can also vote for those that you like best. We will discuss your questions based on popularity as a rough guide, so it's worth putting in your opinions there. We will see you again at 8:05. Until then, see you soon. Welcome back, everyone. Thanks for all the questions we received so far. Please keep them coming, even though we are starting the Q&A soon. Here again, the link, sitp.online/ask. Also, a little reminder, after the talk, we will open our Lock-ins Razor, our regular virtual pub on Zoom, where we can all get together and have a chat. And for tonight, I even might have some incentives for you guys to join. I know you love your cats and dogs. We discussed this with Alice. She's got 2 lovely dogs, but she can't show them during the talk today. But they might make an appearance during the razor tonight. So join in. Let's see whether we can get them on the camera then. Good. So, Alice, let's start with the questions. The first question we have is from Danger Moose. Which are the most and least treatable cancers? Why?
This is a good question. It can be a sad question, especially when I know that there's more people in the audience than might be in the pub, and I can't know what everybody's situations are. Most treatable is pretty much like testicular cancer. Testicular cancer, some skin cancers we're really good at treating. Largely, if you can whack it off, you can treat it quite well. So testicular cancer, you can remove the tumor quite easily, and same with some skin tumors. If you catch it before it is penetrated, now if it starts to spread, then it becomes problematic. But if you catch it nice and early, and again, for both of those cases, it's something you're more likely to notice. You're more likely to catch it early. You're more likely to get that treated quickly, and it can be excised quite quickly and treated really well. In terms of least treatable, some of the classic ones are things like some of the more severe forms of pancreatic cancer we find very, very hard to treat. There are some forms of pancreatic cancer that we treat very, very well, including the one that Steve Jobs had when he was first diagnosed and then decided not to undergo treatment, and ultimately it went down an alternative therapy route and didn't survive. But had he been treated earlier, he would have been done much better. So some forms of pancreatic cancer, it's hard to detect. You don't really get symptoms until much later, and then it progresses quite rapidly. And another one that's quite difficult to treat are some of the more severe brain tumors. Again, you don't get symptoms until quite late on. They develop very, very rapidly, and it's very hard to treat tumors inside the brain, because not only is it hard to get to if we want to start removing the tumor surgically, but it's also hard to get treatments into the brain because we've got the blood-brain barrier. So those are your most and least treatable cancers, but we're making good progress on lots of things. And actually, so when I talk about pancreatic cancer being difficult to treat, if we have this new RAS inhibitor, that might be actually very good for people with pancreatic cancer. So we're always making progress.
Sticking to the hopeful side, Chris N asks, there are some exciting developments in mRNA treatment for cancer recently, but I don't understand it. Could you explain it to a layperson like yours truly?
Ish. So I'm going to assume, so when it comes to mRNA treatment could mean lots of different things. I'm going to assume that Chris is talking about mRNA vaccine type treatments here. And this is quite relevant for the mRNA vaccines in COVID treatment as well. So the idea is that you vaccinate a person against a thing that they need to fight. So in the case of COVID, you give them the mRNA. So when I talked earlier about going from DNA to that additional molecule, that RNA molecule, then through to the protein, we're talking about treating with that RNA molecule in the middle. So we're giving the human body, the cells, the piece of information that it needs to make a protein. Now, if we want to use that as a vaccine, we want to give the cells the tools to build a protein that it believes is alien, that it doesn't recognize, so that it triggers the immune system to react to that protein. It primes the immune system to react to that protein. Now, when it comes to COVID, we'd give the cells the code for the spike protein that exists on the surface of the virus, so that the immune system is primed to recognize the proteins that exist on the surface of the virus. When it comes to cancer, we would give them the cells the tools to build a protein that looks like a protein that is unique to your cancer. So if you have a cancer that has a mutation in a specific protein, you can give the cells the tools to prime themselves for that protein that is unique to your cancer cells, trigger that immune reaction, and then your immune system can do the hard work of attacking the tumor. So that kind of covers that's the mRNA version, but it also covers like the idea of immunotherapies where we're trying to, you probably heard my dog there, where you're trying to trigger the immune reaction to do the job that you want your drugs to do. It's going to kill the tumor cells. We're just using mRNA to do it in this case. So we're not even injecting the cells with the body with a protein from your cancer or from your COVID-19, for example. You're giving them just the tools they need to make their own version of it.
Okay, good. I hope this is not just a bad joke. Backdoor in Espresso asks, urgent question, how do you die from coffee enemas?
So I believe the issue with coffee enemas is that you're getting a massive hit of caffeine into your bloodstream very, very quickly. And if you really overdose on caffeine, it can be really bad for the heart, especially if you have heart problems. So I believe that's the risk with taking a lot of coffee enemas, is that you're overstimulating the heart, particularly if you have heart problems, then you might be at risk of causing issues with the heart.
Okay, good. Katie Crunch asks, to what degree can the body's own immune system fight cancers?
Yes, this is a great question. Broadly speaking, the immune system doesn't really recognize our cancer cells because they're our own cells gone slightly wrong. So if mostly the body's recognizing these tumor cells as part of our own and no need to worry about them because they're fine. There might obviously be cases where it gets so mutated that you might start to get some little reactions. And if they're pumping out lots of chemicals that your body starts to react to, you might get a bit of a reaction. But broadly speaking, they're kind of invisible to the immune system because they look like our own cells. Okay,
makes sense. Camille asks, the failings of the poor patient victims of these scam medicines are not publicized. Is there a database tracking and showing these after the miracle therapies?
There isn't really a kind of organized database, but a few years ago, Michael Marshall from the Good Thinking Society put together a really large database. So he was looking at the people who were fundraising for alternative cancer therapies on fundraising websites like GoFundMe. And he put together an enormous database of everybody who had fundraised for these treatments, but he also went on to look at the media publications of people promoting these fundraising opportunities where they'd been in the local newspapers, for example, and what kind of media coverage there was. And then after he'd done that, he spent a long time, and I helped him with it, to go through all the huge list of people who'd been fundraising for cancer therapies and see if he could find any information on what had happened afterwards. So this obviously is very hard to do. Often, if a person loses their life after going down the alternative medicine route, the alternative practitioners don't want to talk about that. They will just be quietly removed from their testimonial website. There isn't a follow-up newspaper story that covers it. It might be a case of the family members might not want to talk about it publicly anywhere. So it might be a case of seeing if there was a follow-up newspaper story, or seeing if we can find any evidence of their survival, or whether there's been any notification or obituary of their death. So it's hard to put that information together, but it is something that Michael Marshall tried to do for the Good Thinking Society. And some of the data that they uncovered, they also published in the British Medical Journal. And I know that we've given the link to the mods, so the mods should be able to share that link. But just to give you Marsh has actually sent me some of the details. So he spent 6 months tracking just cancer fundraising appeals that we could identify as quackery. So he asked me to help decide whether the fundraising opportunities were genuine cancer science and whether they were pseudoscience, because that can be very hard to understand. He found 475 on GoFundMe and Just Giving. 248 of those he could prove that had been promoted in the media. And And of those 248, he found 78 obituaries or death notices. Some stories claimed that they were doing it because they'd seen a news story of someone else we could identify in the list. So there was this kind of daisy chain effect where there's an article in the newspaper that says this person is going down a fundraising for an alternative therapy. They're excited about this alternative therapy. A few months down the line, you get another patient who says, I'm going to go down this therapy, and I'm going down this therapy route because of person A who came before me, and there's this daisy chain effect. And sometimes person A has already died, and you don't know that by the time these new patients are going through. So it's a massive problem. It's not one that we've recorded as well as we should do, like collectively on the whole, but it's one that, just looking at that snapshot of 6 months worth of data just from those fundraising sites, it's clearly a huge problem that we should be getting more information on, and we're struggling to. So if anybody wants to do that research and fund that research, it would definitely be interesting.
Yeah, definitely. Let's do a change of track. 1939 seems early and progressive for a legal cancer act. Can you tell us more about its history? No.
Sorry. So I can't remember the background to the Cancer Act. I know it's been around for a while. I know. So, it was first legislated genuinely that long ago. I think it's related to when we were starting to make big conversations about how big an issue cancer was. We had a lot of people were starting to get really concerned about cancer in those days, and it was a really big topic that everybody was interested in. And I think that's a big part of why that legislation came in. Unfortunately, it's not prosecuted on as much as it should. There's very few prosecutions under the Cancer Act. It's largely brought forward by trading standards, and they are chronically understaffed and overworked, and it's very difficult for them to actually bring these things through. So as much as it exists as a piece of legislation and we can talk about things breaching the Cancer Act, the reality is that it's very difficult to actually use it to stop people making these claims. We can threaten them with trading standards, and trading standards will get in touch with them and make threats to them, but it's very, very difficult to follow up on.
That's a shame. Okay, Andrew in Peterborough asks, why can these dangerous pseudoscience cancer treatments not be banned?
It's tricky because some of them just aren't. They're pitched as cancer treatments, and we will, at least in the UK, you're not allowed to advertise a medical claim for something that you can't back up for something that isn't medicine. But it's hard because so many of these pseudoscientific treatments are kind of vague. So it'll be things like, we'll take this diet or this juice and it'll boost your immune system. And it's all lots of vague terms. And, well, we're not going to tell you publicly what it is, but if you see us for a private consultation, we'll start to talk to you about it. Then it starts to get tricky to actually legislate that. So it's really challenging to have a blanket ban on anything, because you don't want a ban that's too stringent and that might risk us doing research on really interesting and exciting new therapies. But you also don't want, it's really hard to find the wording on how you ban something that's so vague and hard to describe.
Sounds like it's just one of the dark sides we have to accept.
Yeah.
Okay. Chromium 52 asks, why has the lifetime risk of cancer increased? Simply because we don't die of other causes first?
Yeah, so we're not 100% sure of all of the reasons, because it's clearly like a huge complicated thing. This is population studies, and that's not my area of expertise, population studies, but it's a big complicated story. We think a big part of it is cancer is a disease of old age, largely speaking. The longer you live, the more mutations you are likely to acquire. So if you live longer and our lifespan has increased, you are much more likely to encounter cancer at some point in your life. But there are other elements to it as well. So we know that things have changed in our environment. We know a large portion of our risk of cancers is environmental, and our environment has changed. We've got more pollutants in the air. We've got more. We're living different diets. We're eating different foods. There's lots of different things that are happening in our environment that will increase our risk, and some things that have changed that will decrease our risks as well, of course. But yeah, so it's really complicated. But certainly living longer is a big part of it.
Okay. Good. One of our regulars, Paul Pictacule, asks, would you say cancer in all its multiple forms is the most important disease facing humanity at the moment, rather than, say, heart disease or diabetes?
It's an excellent question. I don't know that I would say it's the most important disease facing humanity. I think it's a question that would have multiple different answers depending on what you're thinking about. Heart disease clearly affects a huge proportion of the population and is something that we understand in a way that we might be able to treat it quite well with the right treatments and with dietary changes or working on other things. But I don't know. It's clearly a big issue and it affects such a large portion of the population, but we also treat it really well, and you can live an entire lifetime with cancer if you get treated well. I would say if we're going to talk about the threat to humanity, I think the biggest issue is more medical misinformation, and that has a much bigger role in cancer than perhaps heart disease or diabetes, because cancer is such a complicated disease. It's very easy for this misinformation to spread and for people to be utterly convinced that the alternative therapy is going to work. But yeah, I care about cancer because it's my area of interest, but I think I wouldn't say it's more important necessarily than heart disease or diabetes or neurodegenerative diseases or anything else like that.
Okay. Next question comes from Liam. Can two different cancers arise around the same time and compete with each other?
Great question. I don't know. Well, I do know in the sense that it's technically plausible. I don't know if we have any examples of that having happened where two completely unrelated cancers have spontaneously been generated at exactly the same time and compete with each other. We know patients can have multiple different types of cancer that are completely unrelated to each other, if you're really unlucky. We also know that one type of cancer can progress through the body and look like another different type of cancer. So, for example, you will often get breast cancer might metastasize to the liver, and then you've got breast cancer, but you've got it in your liver. I would imagine it's possible for two tumours to exist concurrently in a similar space that are very different and compete with each other. But I don't know if there are any examples of that happening. It's a good question.
What would they be competing for? Resources, space,
nutrients? Yeah, all the same stuff that they would be competing with the normal cells for. But when it comes to competing with normal cells, the tumor cells are pretty well developed to win that battle. Okay. But when they're competing with each other, it might start to become a little bit more challenging. And I can imagine a scenario where they just keep each other in check a little bit.
Okay. Good. Question from American Alice. You said that
Alice.
You said that men are more likely to be diagnosed with cancer than women. With trans people, is that due to biological or hormonal differences?
So it's a tricky question to answer because, of course, we don't have the data. We don't do enough research that really properly considers the trans experience and how that influences things that we say are gender related. So there's a major issue there, and I would hope that as we progress, we learn to define our research more intelligently to really understand this. And if we just look at the broad topic, so where we say men are more likely to be diagnosed with cancer than women over their lifetime, we're not even fully sure why that is. So we don't know if that's a biological thing or if it's a very broad speaking gender difference, that maybe a larger proportion of men are more likely to experience certain environmental certain environmental factors that increase their risk. And that would be, a very broad strokes consideration, but still might be playing a role once you get up to that population scale, or whether it's a biological thing. And we do know that there is some data that suggests that women have slightly different responses to some things and men have slightly different responses to other things. But it's still such a mess to understand all of that data. We don't even research things. We don't even research women very well, let alone starting to research the situation in trans people properly in a way that would actually give them the healthcare that they need. So we don't have an answer, but it is a really interesting question. And I would hope it's something that we will start to research more in depth in the future, that we will be able to identify differences both between cis men, cis women, and also then taking into account trans men and trans women as well, and anybody who doesn't identify with either gender.
Do we know whether those differences between rates in men and women are the same worldwide, or are there differences between countries?
I don't know off the top of my head. So I'm not a population biologist, so it's not my area of expertise. But...
Good. Parrot Lady asks, how do you know if the cancer in a specific individual is linked to diet?
We don't. It's really hard to know. We don't even know what it is about, say, for example, smoked meats or red meats that causes the increased risk in cancer. So all we know is that we've done enough studies in enough people that say there's a difference. If you eat a diet high in smoked or processed or red meats, you're at an increased risk of getting cancer. Whether we know, we don't know what it is that is causing that change. We think possibly it might be to do with mutagens that are in the meats. And then certainly we can't know in an individual because we don't know what the kind of diagnostic marker is, if you like, in that situation. So yeah, we've no idea.
Yeah. Okay. Steel Wolf asks, what is the best way to counter the inevitable pseudoscience argument of all cancers were cured 50 years ago, but the drug companies suppress it to make money?
It's hard, isn't it? Because it's your basic conspiracy theory, and I don't think there is countering conspiracy theories. They're not based in rational evidence-based arguments, and it's hard to really say, no, that's not the case. We can talk about it rationally and say it's highly unlikely that drug companies are suppressing the cure to cancer, because in a drug company working in trying to cure cancer, you've got multiple different people. You've got the top level people who are going to be making a mint, but you've got the people who are working on the bench every day just doing the basic science. You might have hundreds of thousands of those across the world. If they know that there's a cure, how are you getting all of those people to keep the secret? And you're not paying them nearly enough for it to be worth it, especially not if they have family members who get cancer that they can't give the cure to, because then the cure slips out. So we can talk rationally about why it's completely illogical, but ultimately it's people who believe that it's a conspiracy theory, and I'm not sure rational arguments are the things that are going to persuade them.
The old saying of you can't reason them out of a point they haven't
reasoned themselves into, yeah.
Sticking to the pseudoscience, Chromium 52 has another question. There is apparently a pseudoscience nonsense notion that cancer is a fungus. What's up with that?
Yeah, it's a really weird one. There's loads of weird claims about cancer, and some of them make sense. So the really common one is that cancer eats sugar. Cancer eats sugar, so to cure your cancer, you should starve it of sugar. And I at least understand where that comes from, because cancer cells do metabolize energy in a different way, and they're dependent on glucose in a slightly different way to normal cells. Now, that doesn't mean that not eating sugar will affect your cancer, because they're also really great, and they're really clever, and they will break down things in your body to get, glucose is just a normal molecule. They'll break down things in the body in order to get the glucose that they need. It doesn't matter whether it came from sugar or not, just because it is a sugar. Your liver can break stuff down to make sugar for itself. But when it comes to fungus, the best argument I've seen basically is that tumours are white.
Okay.
Makes zero sense to me. I can't follow that thought at all. And it's the most bizarre. It's genuinely it's not one I come across a lot, but it is quite prevalent, and I can't even understand how they got to that idea, let alone taught themselves into thinking it was a fungus. So I'm afraid I don't have an answer, but only because I don't understand it myself. I can at least, some of the other bizarre ones, I can at least understand how they got there. Even if they've made a mistake, I can see how they made that mistake. I can't with the fungus one, I'm afraid.
Okay. Would be nice if all cancer turned green. Would be easy to identify.
It would be easy to find, yeah.
Okay, Camille asks, neat talk. What are your takeaways from that pseudoscience cancer conference? What startled or troubled you most? Thanks.
So the one I've actually been to a few pseudoscience cancer conferences. So the one I talked about where I went to see Patrick Vickers give a talk, that was one of the most distressing things I've seen, because he made such bold claims without caveating them at all. He seemed to have no qualms with saying that he could cure cancer, and that conventional treatments, you should stop taking them. And he directly told patients to stop taking their conventional therapy. And I think there will be people in that room who made medical decisions based on that misinformation who will now have died. And that is really, really sad. But I also thought one thing that was incredibly interesting about that particular talk was he talked at length. He actually named a patient, which is incredibly unethical, and obviously I won't repeat it. He named a patient that he was treating, who he said was a famous musician, who, because he was touring regularly, couldn't always keep up to his prescribed treatment, so couldn't always get access to the organic foods that he needed to get access to in order to follow the Gerson therapy to the letter. And he essentially said, I think this patient's going to die because he can't follow our treatment perfectly enough, which in and of itself was pretty abhorrent. To talk about a patient by name in that way was really awful. But also this connotation that if your treatment doesn't work, it's your fault, is a massive issue when you're claiming to treat cancer, because, you know, that's a real problem. And of course, it means that patients don't go on to get the support they need. If they get to a point where I've been trying the Gerson therapy and it's not working and I seem to be getting worse, or I'm feeling really unwell, they don't think to seek additional guidance from a medical professional. They think, I'm not trying hard enough, I'm not doing well enough, it's my fault. And they continue down that path for longer and convince themselves that they should. So for me, that's one of the most distressing things that is quite common to a lot of cancer alternative practitioners. And I've seen a lot of them speak, very few of them, and in some ways it's more insidious because very few of them actually go that as far as Patrick Vickers did. They don't tell you to stop taking your conventional therapy. They tend to couch it a little bit more. Although that could in some ways be more dangerous because you're kind of led, somebody who's less convinced might be more gently led into it. Whereas Patrick Vickers is only going to get the people who are already a little bit convinced. But yeah. It's a common thing, is blaming the patient when things go wrong. Okay.
Moving on to Daniela. I hear all of these new treatments, but every 5 years or so a family member comes down with cancer, and it seems none of those are in clinic yet, or are some?
Yeah, it's really tricky because as a society, we really care about cancer because it affects so many of us. So it sells papers. As soon as there's a new treatment, it gets in all the papers. There's a big splash. We've got the cure to cancer, and it'll be very early days. Your pharmaceutical company wants to put a press release out, and they want to put that press release out partly to show off to their competitors to say they've got this brilliant treatment. But then it starts, of course, they also want to get it into the media because it helps them with their income and their who they are as a company and their marketing and stuff. But the issue is it gets out into the newspapers long before it's actually ready to go into clinic. And it means people are aware of treatments long before they're actually available for people to routinely use. It takes a really long time to bring a new treatment through to clinic and to general use. We need to understand the safety of it. We need to understand how many patients it helps, whether it is better than the alternatives that are available. We need to understand exactly how to administer it, exactly who to administer it to, because everybody's cancer is slightly different. We need to understand a lot of different things about it, and it takes a long time to bring it all the way through to clinical practice. Treatments get through to clinic all the time, and we are making big leaps. But there's a lot that you read in the media that, some of it you'll read in the media that will never make it to clinic because they're telling you about it when it's still in animals. And actually, once they get it into humans, it turns out it doesn't work. So it's tricky. And a big part of it is how we promote it and how we talk about it in the media. It's a big problem.
Yeah. Good. Shantz or S. Hans, not sure, asks, why is cancer pro-inflammatory?
I'm not sure we fully understand this. So we know that it's quite common that there's more inflammation in cancer. We sometimes know that increased inflammation might lead to cancer. Not always, but sometimes. We know that the two are almost inextricably linked, but we don't fully understand why. We've got some theories, but we don't fully understand why. So I'm not sure there's an answer to that one. Yet.
Good. Grady Earthling has a question. Are there any diseases that are almost cancers but just miss out on that classification because they lack some crucial behavior?
I think broadly, so although I mentioned the hallmarks of cancer and I said these are the things that you need to have to make you a cancer, I think there are some types of cancer that haven't quite got there yet. We classify things based on our expectations, based on the science. So you might have a case where you've got a tumor in a location. So one of the things in the hallmarks of cancer is that they are metastatic. Well, we know that we will start to treat something as a cancer, and we would in fact call it a malignancy or a cancer, certainly to lay people, long before it's become metastatic, because we want to get them down that treatment route to prevent that happening. So there's definitely cases where we're not using that as a tick box to call all things cancer, and we try to be more pragmatic and understand common disease progression and understand the cases where things look similar but definitely aren't. So we might have the formation of what we would call a benign tumor, where you've got a collection of cells that have grown a little bit out of control, but then they've stopped. And we know based on other cases of progression that actually them stopping in that way, in this particular form of growth, isn't going to do anything, is unlikely to do anything. So we'll keep an eye on it, but we'll not call it a cancer. It's a benign tumor that is probably going to stay benign, and we'll just keep tabs on it. So I think that answers the question.
Yeah. Okay, Grimbeard has got a question. There's a perception that cancer equals death sentence, which may drive people to quacks out of desperation. Will improving real treatments help counter that?
I think there's a multi-pronged way to help counter that. Yes, there's a perception that cancer is a death sentence. I don't think it's a helpful perception. And I think the biggest issue, rather than focusing on the real treatments, I think the biggest issue is to focus on demystifying cancer. It's a big part of why I give this talk. Demystifying cancer before you get there. Because when you're sat in a doctor's office and a doctor says to you, you've got cancer, you automatically go, or I'm sure a lot of people will automatically go to, it's a death sentence, and be utterly terrified and scared about what that means, and go into levels of distress that are very hard to manage. You shouldn't be learning about what this disease is then. It's such a common disease that if we can really demystify this earlier, that people know, actually, if you tell me I've got cancer, it might not be the worst thing in the world. It might be one of these ones that has a 98% 10-year survival rate. And actually, it's nothing to be scared about as long as we act quickly. But people need to be aware of the situation before they get there. I think once you get into that situation, it's very hard to think clearly and to understand the complexities of it. And demystifying it earlier is going to be one of the big things that will help. And I think that comes from multiple places. So I think educating people early on is helpful, and it's a big part of why I do this talk. But I also think the media has a lot to answer for. And if we can shape how things are discussed in the media, and that's not just the fault of the journalists who talk about it, it's also the fault of the scientists who don't know how to communicate their science to the journalists. And we can try and make this get to a position where people are aware of the situation long before they ever have to be aware of it.
True. Good. We've got a question from Andrew. It sounds like cancer has a lot of traits that make it very hard to fight. How did it become so well adapted without offering any evolutionary advantage?
Depends what you mean by evolutionary advantage. If you're talking about the cell, it's got a great evolutionary advantage. It survives and grows and lives forever. Cancer cells are brilliantly adapted evolutionarily, just not for the organism on the whole. But if you think of each individual cell as an individual cell that is trying to survive as best it can, all these cancer cells are brilliantly adapted to surviving and living longer. So it makes sense to me why you would develop cancers in complicated multi-celled organisms. In the old days, like you go really far back in the past, and everything was single-celled, and it was the survival of the cell that was the most important thing. You go back before that, and it's the survival of the genetic material. So it makes perfect sense that they have an evolutionary advantage. It just doesn't give an advantage to the organism on the whole.
Yeah. Good. Brenda wants to know, how do you actually know what all these pathways are? What sort of experiments were done to find that out?
Oh, this is a great question. And I can't give you an answer without boring you to tears. But between the 60s and the 80s, there was a lot of we started to understand cell signaling and cell biology, and we started to do a lot of really complicated experiments to figure all these things out. And we've basically pieced it together bit by bit by bit. And it's not easy to research to figure this out. And there are some really clever, intelligent, intricate experiments that were done to really tease out all these details. And there's still things we don't know. We still discover new proteins all the time. But those big pathways that we know are really important for lots of cells, we've kind of teased out all those details bit by bit, literally just discovering a new protein and putting it in, like building it up like a jigsaw puzzle. It's fascinating and exciting and really interesting, but way too detailed and boring for a lay talk. So I'm not going to go into that detail.
And I guess we're not done yet.
No, exactly. So there's still more to find, and we discover new proteins all the time. We discover new organelles all the time. Even we discover things we didn't know existed in the cells constantly. There's always something new happening.
Good. Question from Anonymous. Any advice for second-year biomedical sciences student hoping to get into cancer research, please?
I do. I think one of the best pieces of advice I can give you is talk to other scientists. I know it's terrifying to email a scientist out of the blue and say, I'm really interested in what you work in. Can you help me? But my experience of scientists is they're really happy to help enthusiastic new young people coming into their field, and they're super excited to talk about the things they're working on. So one of the best things you can do is read around the things you're interested in. If there's a particular part of your studies that you're fascinated by, if there's a particular lecturer that you have that you're really enthused by, reach out to them and see if you can either chat to them about their work, or if you can go and do some experience in their lab and see what the researchers in their lab are doing. I think that's really important. And it's one of the things that helped me most as a second year student, was reaching out to people in different groups and saying, I'll do it for free. Can I come and do some lab stuff in your work? And some of them, some of them would give you actual work to do. And that would be really cool because you get to do some actual research. And some would say, I don't have space to do any actual research with you, but what I'll do is let you come in and you can shadow one of my postdocs for the day and they'll show you what they're doing. And most scientists are really happy to share their work, and it's a great way to learn how labs work, how research works, and to really get a feel for what that experience is like, because it's not for everybody. And also it helps you build those networks with people who you can call back on later down the line when you're looking for a reference or you're looking for advice on how to get go into a PhD or other things that you might be interested in. So that would be my advice is reach out to people who you admire in the field and ask them for help. They'll always be happy to help, almost certainly, unless they're a dick. Sorry. I went through the whole talk without swearing.
Oh, well. Before I ask the last question, I would like to say goodbye to everybody tonight, because I'm pretty sure my microphone will be cut by our media team once I've uttered the question. So I don't even know whether you're interested in football. Who is going to win on Tuesday? Shantz wants to know, England or Germany?
Well, I would like England to win, but I suspect Germany might win. Yeah, that's my answer.
I'll stay on the 50-50 fence. I don't know.
I think it'll be close either
anyway.
way. For sure. I think they're probably fairly well matched.
Good. I'll say thank you very much, Alice, for this very entertaining and enlightening talk. And also the questions, I think, were very good once again. And your answers were quite interesting. So thank you very much for that.
Thanks for having me.
There. Just a short announcement. Next week, we will host another live edition of the Incredulous podcast. I haven't been able to take note of the guests, so please keep a lookout for those additional details that will be released. I think they might already have been released today or will be very soon. So keep an eye out for that. But it's next week, starting at the same time, 7 p.m. Other than that, anything that's left to me is to say once again, thank you to Dr. Alice, and to wish all of you out there a good rest of your evening and a good week. Short reminder, the Lock-in's Razor is going to be opening very soon. Until then, stay safe, stay healthy, and stay skeptical. Good night.